Okay, so I'm going to be working on a pure bending moment problem of a composite material. And I'm going to be doing this left side right here. So the reason why I chose this problem, I don't see this a lot on YouTube. Usually you find the stresses, but this problem we're finding the maximum moment that this material can withstand. So looking at the cross section, we could do two different things. We can either convert everything to aluminum or convert everything to brass. It's really up to you. What we're going to do first, though, is find the ratio. That would be step one. And we call that ratio N. And what we're doing is we want to see the relationship between the strengths of the material. And so now the module elasticity for brass is 105 and the modulus of elasticity for aluminum is 70. This means that brass can withstand more pressure than aluminum. So how much more pressure? Well, that pressure ends up being 1.5 times as much. And knowing that the stresses due to bending moments is linear, knowing that, we're able to use ratios. So I'm going to be doing case 1, which is the left-hand side. And that is right here. Now, to convert everything to aluminum, we're going to use the ratio N is 1.5. Now, if you think about it, if brass could withstand more pressure than aluminum, it makes sense that this aluminum piece right here and this brass piece right here are going to be able to withstand different amounts of pressure. So to convert everything to aluminum, I'm going to need more aluminum in the brass area, right? Because this brass area could withstand more pressure. So we can't change the height, but we can change the width. So what we're going to do is we're going to get the width of brass and we're going to multiply it by the N ratio, because we're going to need how much more aluminum to compensate for the strength of brass. Well, we're going to need, first let's take the width of brass, which is 30 millimeters, and we're going to multiply that by 1.5 times the amount of brass is the amount that we need for aluminum. And so that ends up being 45 millimeters or 0.045 meters. And that's where we get the dimensions right here. So now that we have our new diagram, we're able to work out this problem. So step 2 would be to find the neutral axis. And we're going to set up our Y and X axis, our positive sign convention axis, in green over here, and in order to find our neutral axis. Now it just so happens, because of the symmetry, Y bar, if you use this formula, number 2, ends up being directly in the middle anyways. So that means Y bar is 21 millimeters or 0.021 meters. And that is where we have this dimension right here. And so that means that over here, this would be 21 millimeters as well. Now the third step is we're going to find the moment of inertia. Remember, we're building upon this formula where it says the stress is equal to the moment multiplied by y, which is from the central axis, or better yet, the neutral axis, to any point, divided by the moment of inertia with respect to the neutral axis. So we're going to use this formula. This is the parallel axis theorem. It's basically you're just going to sum up all of the moments of inertia for each piece, and then you're going to add that to this little area right here times the distance between the neutral axis and the centroid of each piece. So the moment of inertia with respect to the neutral axis, and let's do member number 1 first. That's this member right here. And we're going to do 112 multiplied by its base. We're using this formula right here. Multiplied by its base, which is 45. And multiplied by its height, which is 6 cubic. And then we're going to add the area of it, which is 45 times 6. Multiplied by the distance. The distance from the neutral axis to the centroid axis, which is going to be 21 minus 3, which is 18. So this is going to be 18 squared. That's for the first member. Now notice that member number 3 is going to be the same. What's going to be different? Well, the moment of inertia is still going to be 112.45 times 6 cubed, plus the area is the same, and the distance between the centroid, or the neutral axis, to the centroid of the member is still going to be 21 inches, right? So that means that we can cut a little corner and say this is member 1 and member 3 if we multiply this by 2. Now we're going to add that to member number 2. Again, it's a rectangle, so its moment of inertia is 1/2 base. The base of the middle is going to be 30, and the height is going to be 30 cubed, plus 30 times 30, and the distance between the centroid of the middle member and the neutral axis is 0. So this is going to be 0 squared. So we can conclude that the moment of inertia with respect to the neutral axis is 2. 1 divided by 12. And 45. 6. 45 times 6. And this is going to be 18. Then we're going to add that to cubed. 1 divided by 12. 30. And 30. So that means that we are going to have 244,080, and we were dealing with millimeters to the fourth. Or we could say that the moment of inertia with respect to the neutral axis is 244,080 times 10 to the negative 12 meters. And that's just converting millimeters to meters to the fourth power. 3 times 4 is 12. Bring that up. It becomes negative 12. Okay, so we have all the information. And now it's time to find the moment, the maximum moment that we're able to have. So remember that this is the formula for stress induced by a moment. So therefore, the moment would be equal to stress times moment of inertia divided by the distance from the neutral axis to any point on the member that we desire. But we have to go from the neutral axis. So we are given some limitations. Aluminum's allowable stress is 100 megapascals. And brass is 160 megapascals. Now, if we look at the original diagram, we see that the aluminum stops at these points. And if we recall that the maximum stress is at the furthest distance from the centroid. So if we want to find the maximum stress, we're going to, in the aluminum, we're going to have to make that stress, that arm from the centroid to the maximum point on the aluminum, which turns out to be where the brass starts. And it doesn't change, it's still here too. Still right here too. And that moment arm ends up being 15 inches. Okay? So we're going to have two cases. Case 1, where we're going to find the moment with respect to aluminum is equal to the allowable stress of aluminum multiplied by the moment of inertia and the distance. So if we go up and we find aluminum is 100 megapascals. So we have 100 times 10 to the 6. Moment of inertia is 2,44080 times 10 to the 12 negative divided by, we said that moment arm is 15 inches. So we have 15 inches right here. Oh, meters, sorry. 15 meters. Oh, that's actually 15 millimeters, so we're gonna have to convert that into meters, which makes this like that. So, therefore, the maximum moment, call this max, with respect to aluminum is going to be equal to 1627.2, and we're dealing with newtons times meters. Now let's go up to our diagram and see where the maximum moment for brass would be. Well, if we see if this is the neutral axis, we would have to go all the way to the furthest point of brass, and that comes out to be 15 plus 6, which is 21 meters. So we go down here, and we want case number 2. We want to find the moment with respect to brass, and we want that to be the maximum moment. So we're going to need the allowable stress from brass multiplied by moment of inertia divided by the moment arm. And that comes out to be, let's see what the allowable stress of brass is going to be. 160 megapascals. So that's going to be 160 times 10 to the 6 megapascals multiplied by 2,44080 times 10 to the negative 12 divided by the moment arm. We said the moment arm was 15 plus 6, which is 21, but if we convert that into meters, it'll be 0.021. So therefore, the moment with respect to brass and the maximum moment that brass can withstand, given that allowable stress, would be 160. This is 0.021. $1859.6 newtons per meter. But now, this is where it gets tricky. If we go up to our diagram, notice that this is for aluminum. We're dealing with the aluminum. But brass is much different, right? The brass is a lot smaller than the aluminum. How much smaller? Well, the brass is 1.5 times smaller than the aluminum. And if you think about it, this moment right here is newtons per meter. And if we go up, is not the length of this aluminum longer than the length of the brass? It is. It's 1.5 times as long. So if we take this moment with respect to brass max and multiply it by the ratio of 1 meter of brass multiplied by divided by 1.5 meters of aluminum. And this moment right here, we could say it's with respect to brass, but in aluminum. Oh, but in aluminum dimensions. But in aluminum dimensions. Okay. That makes sense, right? Because yeah, it's 1800 newtons per meter, but not in brass, right? We're dealing with the length of aluminum, and aluminum is a lot longer or a lot wider than brass. So what we're going to do is we're going to multiply by that conversion, and that comes out to divided by 1.5. 1, 2, 3, 9.7 newtons per meter. And so we could say that the moment with respect to brass, the maximum moment is less than the moment with respect to aluminum max. And so to satisfy both conditions where aluminum won't break and brass won't break, we're going to have to use the smallest moment, which is the moment with respect to brass. Therefore, we have the maximum moment equaling 1.24 kilonewtons per meter. There you go. That is the answer.